Welcome to Are You Chemistry GCSE Ready? This playlist takes you through loads of example questions and guided solutions for every single topic in your chemistry GCSE. So it's a perfect way for you to test your chemistry knowledge. If you feel like you need a quick review or you just want the ideal revision companion for these videos, then make sure to download my free chemistry GCSE revision notes. I've linked them in the description below. Or if you're ready, let's dive straight in.
Okay, so our first question here is, what are the three main reasons that lead to reactions not producing as much product as we might expect? So you do need to remember all three. First one, unwanted side reactions. So the idea that actually there's something else being made here that wasn't the product that we wanted or intended. The next one is that the reaction could be incomplete, and that means that some of the reactants are still left at the end. Finally, also some just practical losses. So for example, some of the solution remains in your glassware at the end. It can't be 100% perfect basically when you're carrying out these reactions. Now time to look at some percentage yield questions. So how do we actually calculate percentage yield? Well, you do the actual yield that you get divided by your theoretical yield times 100, and that gives you your percentage yield. So let's do an example to see what we actually mean by that. 10 kilograms of titanium chloride should react to produce 2.526 kilograms of titanium. When we carry out the reaction, we only see 1,950 grams of titanium are actually produced. What is the percentage yield of this reaction? So, firstly, we have got too many things here in kilograms. So we're going to convert that titanium that we produce at the end into grams. So 2.526 times 1,000 gets me into grams, 2,526. Good. Now I'm ready to do my equation. And looking back at the top, we have our actual yield divided by a theoretical yield. So our actual yield is this thing that we say when we carry out the reaction, we see that we only actually make this much titanium. So that's 1,950, and then divided by my theoretical yield is, be careful here, it's not that 10 kilograms, it's this 2.562 kilograms that I converted into grams. Okay. 1950 divided by 2526 times 100 is 77.2%. Calculate the theoretical yield of iron if you start with 20 grams of iron oxide, and we are given this equation here. So let's set up our table. So we've got our murmur, and then across the top I've got that formula for iron oxide, and I've got iron, and the piece of information that I've filled into my table so far is I'm told that my mass M of this iron oxide is 20 grams, so I've put 20 there. Next thing that I can do is I can work out the relative formula mass or relative atomic mass as well of the iron oxide and of iron. So let me do that. On my left-hand side, I have the relative formula mass of this iron oxide. So I've got 56, which is my relative atomic mass of iron, multiplied by 2, and that's coming from that 2 at the bottom, the subscript of the iron there, plus oxygen's relative atomic mass is 16, and that's subscript 3. There are 3 of them, so 3 times 16. And when I add that all together, I get 160. And for my iron, its relative atomic mass is 56. Now to work out the number of moles. So for my iron oxide, I've got a mass, I've got a relative formula mass. So take my mass 20, divide by 160 and get 0.125 moles. And then the final layer that I've added there as well are my ratios. So I'm looking at those big coefficients at the front. I have got 2 iron oxide will give me 4 iron. So I've got 2 and 4 there. And that's not the simplest ratio I could have, because I can divide both 2 and 4 by 2. And so that's equivalent to a ratio of 1 to 2. So now remember, I take that number of moles that I have of this iron oxide and I use it and the ratio to figure out the number of moles of iron. So 0.125 divided by 1, 0.125, multiplied then by 2 is 0.25 moles of iron. Good. Double the moles of iron as iron oxide. Then finally, to figure out the mass of iron, then I take my relative atomic mass multiplied by the number of moles, and that gives me 14 grams of iron. Okay, how do we calculate atom economy? So we have mass of desired product over total mass of products times 100, which is equal to mass of desired product over total mass of reactants times 100. Now, why are those two the same thing? Well, it's to do with the conservation of mass. You should have the same total mass that you put into your reaction as to what you get out. Hence, the total mass of the reactants is the same as the total mass of the products. So let's have a go at this in an example. What is the atom economy of hydrogen in the following reaction? And we're given some relative atomic masses. So let's have a look at our left-hand equation to do this one. So we've got mass of desired product, which is my hydrogen, which comes out the end, and that's 4H2 divided by total mass of the products. So that's my CO2 plus 4H2 times 100. So on the top, I get 4 times H's relative atomic mass is 1, but there are 2 of them, 4 times 1 times 2, divided by 12, that's my relative atomic mass for the carbon, part of the CO2, plus, and then there's 2 oxygen, so 2 times 16, and then plus, again, this 4H2, 4 times 1 times 2, and all of that times 100 equals 15.4%.
Just before we go into the tips and tricks section, if you do want some extra advice to getting that grade 9 for your GCSE, then why not download my free 20-minute exam success guide? Just click on the link in the description below. I'm going to give away all of my best advice and secrets, and completely for free, so why not?
Okay, tips and tricks for this section. Make sure you're confident on your reacting mass calculations, because some percentage yield calculations are combined with those. Okay, so that's kind of like what we did with the theoretical yield part, and then maybe using that to calculate a percentage yield afterwards. Not for IGCSE, but for anybody else, any reaction that produces one product will have an atom economy of 100%. Careful when you are calculating your atom economy. You do need to take into account those big numbers before your formulas, okay, and you do need to multiply those in as well.